Dear students, today we are going to learn about the vias in printed circuit board. We have used the vias in our previous videos using KiCad. So now we are going to discuss different types of vias, what actually vias are. So let's just start this. So vias are actually vertical interconnect access. These are the plated through holes in a printed circuit board that is used to route a trace vertically in the board from one layer to another. A via is a small drilled hole that goes through two or more adjacent layers. It allows the signals and power to travel between layers. As the circuit between the layers of multi-layer PCB are independent of each other, vias are important means to establish interlayer connections. So types of via based on position in stack up. These are depending upon their position in stack up. Vias are commonly classified in three types. The first one is through hole via, the second one is buried via, and the third is blind via. So let's discuss these three types one by one. The first one is through hole via. This goes from outer layer to outer layer of the PCB. The through hole via is the most common type of via in PCB manufacturing, which connects the inner and outer layers and passes through the entire board. It is usually used for internal interconnections of the board or as a mounting hole for components. The second type is buried via. This goes from inner layer to inner layer, and these are not visible on the PCB if we see the PCB with the naked eye. A buried via connects at least two inner layers and it's not visible on the outer layer. It is designed mainly to connect inner layer signals, which can reduce the chances of signal interference and are suitable for high density interconnects. The third type is the blind via. These vias goes from outer layer to inner layer. A blind via stands from one side of the outer layer and connects at least one inner layer but does not pass through the entire board. Therefore, blind vias are exposed only on one side of the board. In PCB design, blind vias can help free up some extra spaces and are commonly used in BGA assembly and HDI PCBs. BGS stands for ball grid array. Now we will discuss the vias based on function. The previous three types are based on the position in the stack up. Now we are going to discuss the via types based on the functions they perform in the PCB. The first one is the micro via. The second is thermal via. Third one is via in pad. And the fourth are the stitching vias. So now we are going to discuss these four types one by one. The first one is micro vias. Micro vias are used exclusively on printed circuit board with a high number of interconnections. Micro vias have a typical cone shape, an aspect that greatly simplifies the internal wall plating process. Each single micro vias can cross at most two adjacent layers. Micro vias can be overlapped in a stacked configuration. Micro vias can have an alternative configuration, that is the staggered one, in which the micro vias placed on adjacent layers are offset from each other. The third one is the blind micro via. Blind micro vias extend from one side of the outer layer. So micro via benefits. The widespread diffusion of mobile and portable devices such as smartphones and wearables have resulted in evolution of microvia from single unit to more complex structure composed of multiple microvia. The microvia affects the PCB size. Compared to normal via holes, microvias have the advantage of reducing the PCB size in board with a high number of connections. Microvias are particularly useful in some applications such as BGA breakout. In audio circuit, microvias reduce crosstalk phenomena, and in high speed and high frequency application provide better protection from electromagnetic interference. The second type of via that is based on the function of via are the thermal via. As the name suggests, these are related to the heat. Thermal vias are simple plated through holes that are located under a surface mounted heat source in a printed circuit board that allows heat transfer. The via establish a low thermal resistance path from top copper to the bottom side of the PCB. As you can see in the picture over here, the thermal vias are placed under the component so that heat can be transferred to the other side of the PCB. One via cannot dissipate heat well and generally requires vias array. So over here you can see that there are number of vias that are arranged in an array so that they can efficiently transfer heat. Active components such as power electronic devices including MOSFETs, diodes and power modules, they are high performance microprocessors and high frequency components develop a considerable amount of heat that can be better dissipated through the adoption of thermal vias. Most of the printed circuit boards are based on FR4 material that however have a high thermal resistance. As a result, heat builds up near the bottom of the component, resulting in high temperature rise and potential formation of hot spots. Thermal vias placed in direct contact with the active components favor better heat transfer, allowing the component to operate at a lower operating temperature as close as possible to ambient temperature. The thermal vias behave like a tube capable of transferring heat from a component placed on one of the surface layer towards the innermost layer. Thermal vias also have some inductance, so it is preferable to place more vias in parallel connecting them to the ground plane to provide a return path with lower inductance. The thermal channels are also covered with a solder mask on the back side of the board to prevent the solder from going through the holes. The third type based on function is via in pad. Via in pad is the design practice of placing a via in the copper landing pad of the component. These vias can either be standard through-hole vias or micro vias, but their position in a surface mount pad makes them unique. Over here in the picture you can see that with this one a C1 capacitor we have a traditional via, and on the U1 at pin number 1 we have that via in pad. So via in pad is actually placed inside the pad. Compared to standard PCB via routing, via in pad allows are designed to use smaller components pitch size and further reduce the PCB's overall size. With component manufacturer pushing smaller parts every year and the demand from consumer for smaller devices, the usage of via in pad by hardware engineers have become more common practice. So now we will do a comparison between the via in pad and the traditional via. So we will discuss traditional via and via in pad. In traditional via, the signal is routed away from the pad and then to the via, while in via in pad, the drill hole for the via is inside the pad. Traditional via, this allows the application of solder mask to prevent solder paste from wicking into the via during the reflow process. And in via in pad, you cannot tent the via with solder mask. In the coming slides, we will discuss about the tenting of the via. In traditional via, the traditional via prevents a situation which can cause the pads and component connection to fail due to insufficient solder. While in via in pad, leaving the via open to allow the paste to wick into the barrel will cause reliability problem during manufacturing. So when should I use via in pad? When you need to fit a large number of components and traces in a small area, via in pad design can help you save PCB space by reducing the number of vias on the surface of the board. Via in pad design can help transfer heat away from the heat generating components such as power devices by providing a direct thermal path to the copper plane. Another benefit of via in pad is for high frequency application. Via in pad can be useful for controlling the impedance of the connection and improving signal integrity. The fourth type, based on the function of via, is the stitching vias. Stitching vias are simple structure. They are periodic array of vias that are generally grounded across the PCB stack up. They serve as connectors for essential zones like ground planes, power nets, and signal path. So purpose of stitching via, the first one is ground plane continuity. In a multi-layer PCB, ground planes may exist on different layers due to the complexity of the circuit. These ground planes are typically interconnected to provide a consistent ground reference. However, due to factors like signal trace components or other design considerations, gaps can occur in the ground plane. Gaps interrupt the continuous ground path, potentially leading to undesirable effects like signal interference and EMI. So in this case, stitching vias are used to bridge these gaps in the ground plane continuity. Stitching vias create a conductive pathway that effectively joins the ground plane on different layers, even though they might be physically separate. The second purpose of stitching via is reduce heat dissipation. When a current flows through a conductor such as a trace or via, a certain amount of heat is generated due to the resistance of the material. By strategically placing stitching vias, designer can create a pathway for heat to flow from areas of high heat generation to areas where it can be dissipated more efficiently. This helps in spreading out the heat, preventing localized hotspot, and maintaining more uniform temperature across the PCB. The next purpose is in the reduced inductance. When high frequency current flows through a PCB conductive path, they can experience increased inductance due to physical layout and properties of the conductor. This inductance can lead to voltage drop and signal integrity issues. Stitching vias provide short direct route from the current to travel between different ground or power planes, bypassing the longer and more inductive routes. So layout tips for stitching vias. The first tip is that surround with copper fill. Enhance grounding by developing stitching vias with copper fill on both top and bottom layers. This practice solidifies the connection to the ground plane. The second tip is placement at corners and edges. Corner and edges of a PCB are prone to high inductance. Stitching vias are most effective when strategically placed in these areas to reduce inductive effects. The third tip is that you have to uniformly distribute this. Distribute stitching vias as uniformly as possible throughout the PCB to create a consistent low inductance path for currents. The next topic in this video we'll cover is the via covering process. The first thing is the tented via. The second topic is the plugged via, and the third is uncovered via. So let's start with the tenting of vias. Tenting via is the process to cover the annular ring of the via with solder mask to achieve insulation. It is important to ensure that the annular ring is fully covered with the solder mask and the solder mask is thick enough to avoid accidental short circuit or contact with the circuit. The next is via not covered, means that uncovered vias. When you choose the via not covered for your PCB design, it means both the via hole and the annular ring will not be covered with the solder mask. These uncovered vias are usually used to debug the measurement signals. Also, leaving vias uncovered has other advantages. For example, it can increase the heat dissipation area, which is conducive to heat dissipation. The problem with this uncovered via is that it is easy to cause a short circuit. The third one is plugged via with solder mask. Actually, in the plugged via with solder mask means that the via is filled with the solder mask material. Via plugged with solder mask is the process to prevent the solder ball from popping out to cause a short circuit during wave soldering and avoid flux residue in via hole. Generally, if the board has a BGA assembly, it is necessary to select the mask plugged vias. The next topic we will discuss now is the components of via, that what are the components with which that via is made of. So the first thing is the barrel, and the second part is the pad, and the third is the anti-pad. So what is the barrel? This is a conductive tube that fills the drill hole, creating a connection between the top and bottom of the board as well as the inner layers if they are present. The second part is the pad. The pad is a circular copper area, also called the annular ring, that connects or links the end of the barrels to the trace or components. The third one is the anti-pad. Anti-pad, this is a hole that separates the barrel and the non-conductive layers. It is a wide area that restricts unwanted signal traces from connecting to a particular plated hole. Now we will discuss about the via size. A very simple rule of thumb is that a via should have the same amount of copper as a track. Since via tends to be round, their diameter should be around track width divided by pi. However, because of the way PCBs are produced, the thickness of the copper in a via is thinner than on the PCB tracks. I prefer to keep via diameter at least half the track width. Actually, the track width should match the circumference of the via. So in that way you can flow approximately exact amount of the current through via as the track can withstand. The next is the current capacity of the via. The primary purpose of via is to transfer electrical signals from one layer to another in multi-layer PCBs. If current does not flow through a specific via, the interconnection between layers is lost, and any one open in a net means the board is unusable. The general current capacity equation is that current capacity is equal to K into delta T into B1 and then A into B2, where I denotes the current in ampere, delta T is the temperature change with respect to ambient temperature, A is the cross-sectional area in mils, K is the correction factor, which is equal to 0.024 in internal conductors and 0.042 in external conductors. Internal conductor means that the track that is going on the inner layer of the PCB. Right? External conductor is the track that is traveling on the outer layer of the PCB. B1, B2 are 0.44 and 0.75 respectively. So to summarize up all what we have studied in this video is, first we have discussed what is a PCB via, that we have seen that it is a vertical interconnect access that connects different layers of the PCB with one another. Then we have discussed types of via based on position in stack up. We have seen that there are three types of via based on position in stack up, that are through hole via, then we discussed about buried via, then we have discussed about blind via, and then we have seen vias based on functions. So there are four types of vias that are based on the function. That number one is micro via, then thermal vias, via in pad, and stitching vias. After this we have studied via covering process, in which we have studied about the tented vias and plugged vias and uncovered vias. Then we have seen that components of the via. In components of via we have seen that we have three components. Number one is barrel, then number two is pad, and number three is anti-pad. After this we have seen the via size, that the via size in a simple word you can recognize that, in a simple word you can understand that the circumference of the via should be equal to the track width. Then we have seen the current capacity of via. So thank you so much. Hope you have understood about the PCB vias in printed circuit board.